Hello, everyone. We're going to do the second section on robustness today. This is a fun section. We actually have seen all the mathematical pieces that we need to make this work. What's great about this particular section is that you're just putting together lots of ideas from the previous lectures to do something that I think is really cool, which is correct the variance of a working model that will give you the wrong variance. So we talked, so let's just sort of get oriented about where we are. So we're talking about robustness, which means we have a working model, and that working model is not necessarily the true model. And you take observations x1 through xn from a particular model that has a functional form of which you think you're interested in theta. And in reality, you're actually selecting observations from some distribution that you have no idea what that form is. And what we learned in the last section was that by maximizing the log likelihood and using that to select our parameter, so that's this piece here, right? This says, okay, my MLE is going to be the parameter that maximizes the log likelihood. What I'll get in the limit, what this thing converges to, what I end up with if I have lots and lots of data, is the parameter that maximizes the log likelihood. But the expected log likelihood, that's the key. So the basic idea here is that you're taking the average log likelihood in the sample, and so then you end up taking the average log likelihood in the population, and you're taking the log of the working likelihood, but you're doing it when the model is wrong, right? You're doing it under the true model. And we saw some examples about how we did that. Like in some cases, we got an MLE of X bar, and that would converge, of course, almost all the time to the expected value of X, but under the true model. And of course, we know this already happens by the law of large numbers. It's a pretty simple application of the law of large numbers. But the fact that it happens in a particular model is also great. So if I have a working model, the Poisson model, and I want to estimate the mean of the Poisson model, it's lambda hat, turns out to be X bar. This will give me the right answer. It'll give me the mean of the unknown distribution, even if my Poisson model is wrong. What happens is that the variance of that Poisson model, because the mean and the variance are assumed equal under the Poisson distribution, the working model will give you the wrong variance. So today we're going to talk about how we clean that up. And that's the cool part. So we have theta n converges to this thing. We are going to assume now that I want theta g. And part of the reason is because the MLE will converge to theta g. I have to want it at the end of the day. If I don't want it, there's no reason worrying about the variance. I'm in the wrong place at the wrong thing. And so that's what we're going to look at how I get that theta g, particularly the variance today. One other piece, just to remind you, we also showed that maximum likelihood was the same, right, as finding the working model that's closest to the truth in terms of Kolbeck-Leibler divergence. Remember, we had this little thing. This is f of theta, and you would get a series of theta 1, theta 2, theta 10, and you'd end up somewhere, and maybe you end up here at theta hat infinity, and that's closest to your working model G here in terms of Kolbeck-Leibler divergence. So we're a couple ways to think about the same thing going on. This is important to be a little bit flexible. It's good for us to understand what the process is here. So what is theta g? Well, you just have to compute it directly to figure out what it is. And very often theta g is going to be a function of some moments, like the expected value of x, the expected value of x squared, the expected value of log x, et cetera, et cetera. There are no parameters in G because it's just G of X. So there's no theta to learn about because theta is the parameter that indirects your working model. And so learning about theta G here means learning about its moments most of the time. We'll see how that works out. The most common case is this, and usually learning about means is good. In a regression setting, you're modeling the mean, so almost all regression parameters are related to something like this, which is also very helpful. So let's go on and talk about this. Let's see. We saw one case where the MLE was equal to this thing, was equal to E to basically this inside piece here is X bar, E of X bar on the log scale plus some junk. And of course, this is not going to converge to the true mean. So in this case, this was a log normal working model where we transform the data. We don't get the right answer. And I would encourage you to try this. Take some data, take the log, take the mean, right? And then see if you can get back to the true mean here. And what you'll find out is you can't, right? Because that's a Jensen's inequality, right? You're taking the average of the logs, and you can't just exponentiate that. You can't just do this to get back to the averages because the log doesn't come out of there. Okay, so that's a Jensen's inequality problem. For now, let's just go back. Sorry, I'm digressing a little bit. And let's assume that I am interested in whatever I'm going to end up in getting. Okay, and so what we're going to talk about today is actually what's the variance of theta hat n, and how do I get the right variance as it converges to that thing. So let's go back to our Taylor series expansion because we've done everything that we've needed to do mathematically. And let's see what the pieces of this are. So remember, we're tailoring expand the score function. So the score function, if you recall, is 0 by definition, right? This is 0 by definition because you're plugging in the MLE. And I'm going to Taylor expand this around the true score function at the true value, which is what I want. And then by Taylor expansion, I take the derivative of the score function, which is this guy. So I have two derivatives, and then I look to see how far I am from the truth. And then I have some remainder. And of course, that remainder would follow similar patterns. So it might be that squared over 2 times L prime 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 over there, etc. Okay. We're going to assume that these guys go to 0. So we're going to assume that all this remainder here goes off to 0, so I don't have to worry about it. All right. So assuming the remainder is 0, I can rearrange these pieces. So what am I going to do? I now have 0 is equal to this piece here. And so I can solve for this, and this is what I get. So I got this piece is equal to these ratios, right? So basically I take this over to the other side. I have theta hat n minus theta is equal to minus L prime n theta over L double prime n theta. Right? And then all I've done here is I've multiplied by a square root of n. I have the really cool square root of n here. If you remember that, right? Because I'm multiplying by let's see, let me get rid of this and let's see if I can make it a little bit clearer. I have 1 over the square root of n times 1 over n, which is equal to root n. So that's that piece. And then I have what's interesting about this is that this thing right here, I'm interested in this quantity because this tells me the sampling distribution of the MLE, theta hat n. Well, why do I need to know the sampling distribution? Well, theta hat n converges to theta. So that means theta hat n minus theta will converge to 0, right? And so this is going to be very hard to examine because it's too small. And so I actually need to make this thing bigger like that. And of course, that's the idea. So then this changes on this side, and we'll get to what that changes in a second. And the way you can think about this, and I'm running out of little space here, but the way you can think about this is you can say, well, suppose I take x bar minus mu and I multiply that by root n. That thing is always going to have a constant width because it's normal 0 sigma squared. So that width of that histogram, think histogram here, is always going to be the same no matter what your sample size is. That's what's super cool about this. All right. Let me go back now and let's go back to where we were. So we have this, we're interested in the sampling distribution, and that sampling distribution is equal to part piece number 1 over piece number 2. So let's see what those pieces are. And before, we had piece number 1 went to I theta, and piece number 2 went to I theta squared. And that was because G is equal to the F. The true working model is equal to the false working model. I'm not going to make the assumption that the true model is correct here. And so because I'm not doing that, I want to see where 1 goes and where 2 goes when G is not equal to F. And so I'm going to leave it general. So the top, this is number 1 right here. Right? This is number 1, which I'm calling B right here, B. The top is, this is going to converge to this guy here, which is the expected of the score, expected value of the score function squared. So this is the variance of the score function. And the bottom here goes to this guy, and this is the expected value of the second derivative. So this is the curvature of the score function. And if G equals F, so if it's going to turn out if and only if G equals F, then it's going to turn out that A is equal to B, and we're going to be in good shape. If G is not equal to F, then it's going to turn out that A is not, then it's going to turn out to be A is not equal to B, and we have a problem. So let's see how this works. We got a lot of moving parts going on, but this is the key. This is the key piece here. And let me rewrite it. Let me rewrite it down here where we have some space. And so basically it's root n, the sampling distribution of the maximum likelihood estimate goes to a normal 0, and its variance is now B over A squared. And we have to find out what B and A are. And in fact, they're just variances. This is the variance, B is the variance of the score function, and A is the expected value of second derivative. We've computed these things before, and they've always turned out to be equal. But when the model's not true, they won't turn out to be equal. So let's go on to the next page here and see what's going on. All right. So what happens here? How do you get that result? Well, this is the top part, right? This is the top part from the previous result. And this is the bottom part. If you look, right? If you look, this is the top. We called that number 1. This is the bottom right there. So this is the top, number 1. This is the bottom, number 2. So this is the score function, and I can rewrite the root n to show that this is basically root n times an average, right? This is an average. So this is root n times average of some random variable y. So that's going to converge to a normal distribution with some mean and some variance, and the variance I've just denoted by B, nothing special. I'm just using B to represent it. And then I have here now just a mean here. And so that mean is going to converge to some number. That number is going to be important. It's the expected second value derivative, but I'm just going to call it A. And we showed by Bartlett's inequality, this was, and we showed before that if the data actually come from F, so if this is basically if I don't want to say it like that. Let's say it is true F equals G, but F is kind of fixed here. So I'm going to say if the true model is equal to the working model, G equals F, then B which is this thing, is equal to the information, and A, which is this thing, is also equal to the information. And so they're equal. So then A equals B. And then so B over A squared is 1 over the information, right? Because you have information over information squared, which is 1 over the information. And so that's what we did before. And we said, oh, look, A is a shortcut, remember? This is a shortcut for calculating B, which is the variance of the score function. Right? So these things were important. I'm going to change my color here. But now let's see what happened if F and G are not equal. So if X is equal to G, okay, and so G is not equal to F, then these things are not equal. And the variance that you want, so B over A squared is a variance that you want. This thing, you just have to calculate by looking at the ratio of this piece and this piece. And what this means is that theta hat minus theta n squared over root n converges to normal 0 B over A squared. And so you'll get your confidence intervals, you'll get your variance from this, but this is the key variance, whereas you might be assuming this. The key here is that this is if you assume F equals G, and this is you assume G, you don't know, is related to F. So this will reduce to this if G is equal to F. But otherwise it doesn't reduce. And so now we can kind of play with this and compute this thing and see what it is. This is going to be a natural variance correction. So this is a natural variance correction. If you like that, if that's helpful, that's good. I just totally made that up, but that is what it is. So let's go on to the next page and let's see what we have. I'm just going to repeat things and then we're going to do an example. So A and B are these important quantities. We're going to estimate them. We're going to replace their expectations with sample averages, right? Because that's how we estimate things statistically, right? So this is the average squared score function, and this is the average second derivative. Because I have B over A squared, this result is often written in a pretty funny way, because a lot of times these are matrices or vectors. And so you end up with something that looks like this because you have to take the inverse. And so this looks like that. And this looks like a sandwich, right? You've got 2 pieces of bread and some cheese in there if it's a veggie sandwich, right? Right. And so you eat that. So this is called the sandwich estimator. And it's the famous robust variance estimator. And it's literally called the sandwich estimator. That's how people know it and understand it. Typically the variance, we don't know what it is. So we use the estimates A hat and B hat. And so here's, for example, how you would do that, right? If in fact they're not vectors, and you're not estimating several parameters at the same time, you're estimating one, then these are all scalars. So this becomes your variance, and then this whole thing is normal 0, 1. You're all set, squared away. All right. The key thing here, one thing that I love about this is that A and B, the estimates of these things, depend only on the working model and the data. So you can compute them from the data. So you can go get these. So you can figure out, even if you don't know the true model, you can still compute them. And then you can use A and B to get the right variance of the score function, even if you don't know the true model, which is cool. The ratio A to B gauges the degree to which Bartlett's second identity fails. And this ratio can be used to adjust the likelihood function to make it robust in large samples to departures from the working model. So let's see how we do that. The robust adjusted likelihood function is literally just the likelihood function raised to this fraction. So you remember we have B over A squared. And if you think about 1 over A as the model variance, right? What you want to do is you want to, and the model variance is wrong, you want to multiply it by an adjustment factor, and that's this. This is the adjustment factor, B over A. And then the model variance times the adjustment factor will give you the right variance. So that's pretty cool. And so what we do here then is we're taking the curvature of the likelihood and we're making it stronger or less stronger, depending on what A over B is. Notice this is the flip A over B, and it is supposed to be A over B. So let's see how this works. I think it's too many unknowns. Let's take a look in a particular case. So I'm going to change the color here. So I have a Poisson data. So my MLE for the Poisson is X bar. My score function, which we've done a number of times, is this, and the second derivative of the score function is that. And so if I wanted to estimate the variance of the score function, right? So this is the variance of the score function. I am just going to actually take the average score function squared. That's it. And the interesting thing about this here is that this piece here, this guy here doesn't depend on I, so they can come out. So here it is, right? It comes out squared. And then you get the sum of squares up top here. You get this piece and this piece. So this should look like 1 over X bar squared times S squared sample variance, but the sample variance is divided by n minus 1, and then I got to multiply by n minus 1, so then I get times n minus 1 over n here. Okay, that's what that piece is. If I looked at the second derivative, if I come over here and I take the average of that thing, this is a little bit more straightforward. This doesn't depend on the data. This comes out, and then I'm summing up these x's, which I get x bar, and so the whole thing is just 1 over x bar n. And so this looks like the model variance for Poisson, right? So for a Poisson distribution, if x is distributed Poisson, lambda, the expected value of x is equal to lambda, and the variance of x is equal to lambda. And we don't know what lambda is, right? So we'll put in the MLE. We'll do lambda hat, which in this case is x bar. So we got x bar for both. Whoops, go away. All right. So if I take the ratio of these things, I get something pretty clever, which is A over B. I take the ratio and I just get this, which is literally the variance under the model to the sample variance times a small little tiny little correction factor that I don't care so much about. That will go away. So all my correction factor is it's saying, hey, how is the model variance compared to the estimated variance in the sample? And if this ratio is close to 1, then you don't change. If this ratio is close to 1, then you don't change the likelihood, right? So you basically take the likelihood function and you raise it to whatever that ratio is. And if that ratio is close to 1, you're not changing the likelihood function. If that ratio is big, then you change it. And I have I'm pretty sure I have some functions in R that I will show you in class that will draw these things. But you could, I mean, this is a no-brainer. This is easy to draw, that you could draw data from a normal distribution and see how that behaves. All right, let's do it with the normal working model. Let's see, what do I want to do here? Okay, let's do the normal working model. So the x's are normal theta sigma squared. The variance is fixed. The MLE is our usual mean. This is our score function, and this is our second derivative. We've seen these before now. So I can calculate the variance of the score function. That's B. Here's this thing. It's just algebra at this point. And here's A, which is the model base variance, which is 1 over sigma squared. And so my ratio, right, is A over B is just the ratio of the variance to the sample variance. And so here, don't forget, we're taking the variance fixed. So this is something like 10 over S squared. So if the sample variance is close to 10, you're good to go. If the sample variance, is, 1, then this is going to be a major correction factor. This is going to really reduce things. Okay. Here's that reduction piece, right? That's that up there. And then you can, of course, do a lot of cross multiplying here and come out with something that's reduced. So the take-home message here is that the trade-off, the adjustment ratio, A over B, is simply the ratio of the estimated model variance to the sample model variance. That's it. So all you're doing is you're computing the model-based variance to some robust estimate based on the sample, and you want to adjust these things. Okay? And the variance is inverted to information, so that's why I have this inversion here. So this goes up here because I got information, and this goes down here because I have information. Variance and information are inverted, right? Just like variance and information are inverted, right, like that. Okay. So the other interesting thing is raising the likelihood ratio to a particular factor doesn't change where it's centered, but it does change the curvature. So if you've got a likelihood function that looks like this, and then your model says, oh, you know what? Your model is overly precise. It's too precise. Or then you raise this thing to a factor less than 1, you're going to get this. When it says, oh, I raise it to a factor greater than 1, that means you're underestimating the variance. You'll get a likelihood function like this. And so it's the A to B ratio that will determine these various things. It's actually nice and clean. So we can do some examples. All right. I'm not going to go on to the next one here, but I am going to encourage you to, if you're not quite as comfortable with this, take some data. You can draw this. This isn't very hard to draw. You can generate some data from a normal distribution, mean, 0, variance, sigma squared, and you can compute this. And then what you can do is you can take this sigma squared and this sigma squared, and you make them different. So your model assumes that this is, say, 10, but you're going to generate data from something that has a variance 2. And then what you'll see is this change. Then you'll see this change here happen. So give it a try. See if you can make it work. And I'll see you in class on Wednesday.